Welcome you all for the online class on Control Systems Engineering. In today's class, we are going to see about electrical analogous to mechanical rotational system. Under this, we have two analogous circuit, torque to voltage analogous circuit as well as torque to current analogous circuit. So in the previous lectures, we have seen how to find the electrical analogy of mechanical translational system. Okay. Now today we are going to see how to find the electrical analogous circuit for mechanical rotational system. Okay. So now we have to consider the mechanical rotational system as well as electrical system. In mechanical rotational system, the input will be a twisting force that we know, that is torque. Okay. And the output of the input for this electrical system will be an voltage signal or current signal. Similarly, the output of mechanical rotational system is the angular displacement theta, isn't it? For electrical analogy, we are considering rate of change of angular displacement, that is omega of t. Okay, so rate of change of angular displacement is nothing but angular velocity, that is nothing but omega of t. Okay, similarly, the output of electrical system will be either voltage or current. If we consider the input of electrical system as an voltage, then the output will be current. When we consider the input as an current, then the output will be considered as an voltage. Okay. So similar to the input as well as output, we have to convert each and every element of the mechanical rotational system into its corresponding electrical component. Okay. So when we transform the input torque of the mechanical rotational system into an voltage signal of electrical system, you will be having an analogy that is nothing but torque to voltage analogy. Okay. When we transform the input torque of mechanical rotational system into an input current of electrical system, we have an torque to current analogy. Okay, now we are going to see each analogous circuit. So listen, first one is an torque to voltage analogy, that is also known as T to V analogy. Okay, so here we are going to convert a mechanical rotational system into electrical system by using a torque to voltage analogous circuit. Okay, so first we have to consider the mechanical rotational system. What about the input signal for mechanical rotational system? That will be a torque. Okay, so torque will be represented by a capital T, or simply we can represent it as capital T. Okay, instead of capital T of T, we can represent it as capital T. Now the input for an electrical system will be an voltage, because we are considering torque to voltage analogy. Then what about the output signal for mechanical rotational system? That is rate of change of angular displacement. That is nothing but angular velocity, which is represented by omega. Okay. Now the output for the electrical system will be an current, because input is voltage, so the output will be an current. Okay. Now we have to transform each and every element of the mechanical rotational system into the corresponding electrical systems. Okay, so first we are considering the first component, that is nothing but moment of inertia of mass J for this mechanical rotational system. Okay, we are considering an ideal moment of inertia of mass which is having negligible friction as well as negligible elasticity, that we know. So due to this moment of inertia of mass, there will be a single opposing force for this mass. This mass will be connected to an fixed surface at one end, as well as other end of this mass will be free. At the free end, we are applying a twisting force, that is nothing but torque. Okay, so due to this twisting force, there will be an angular displacement, that is nothing but theta. Okay, along the same direction of this torque, we have an angular displacement, that is nothing but theta. So along the same direction, there will be an angular velocity that is represented by omega. Okay, because in analogous circuit, we are considering rate of change of displacement, that is nothing but omega. Okay, so in addition to this theta, we have to represent this omega also. Okay, now this applied torque will be opposed by opposing torque due to moment of inertia of mass, that is represented by Tj, T suffix j. Okay, here there will be an absence of TB as well as TK. Okay, Now, using Newton's second law, we can find the torque which is acting on the body. That is, applied torque will be equal to the opposing torque. So here there will be a single applied torque as well as single opposing torques. So the capital T value will be equal to T suffix J. Okay, this Tj is nothing but an opposing torque. So what's the formula for opposing torque? Due to moment of inertia of mass, Tj will be equal to, that is the formula. Okay, so Tj will be equal to J into d square theta divided by dt square. Okay, this we know. So now we are going to write this equation in terms of angular velocity omega. Okay, so for that we have an equations. Listen here. So here, similar to the linear displacement as well as linear velocity in mechanical translational system, here we have an relation between angular displacement theta as well as angular velocity omega. Okay, that is rate of change of angular displacement is nothing but angular velocity omega. Okay, so now if we are integrating this equation on both sides with respect to t, we get the above equation. Okay, theta is equal to integral omega dt. Similarly, when we differentiate this equation with respect to t, we get the below equation, that is d square theta divided by dt square is equal to d omega by dt. Okay, similarly, we can write d square theta by dt square as d by dt of d theta by dt. Is it right? Now, instead of d theta by dt, using the above equation, we can write it as omega. Now, d square theta by dt square is equal to d omega by dt. Okay. Now, we can substitute the value of d square theta divided by dt square as d omega by dt. Okay. So, now capital T, that is the input torque, will be equal to J into d omega by dt. Okay. Now, this should be converted into the corresponding electrical component. Okay. So, here we are using inductor. Okay. Only when we are using an inductor here, we will get the same or the similar equations here. Okay, in electrical system. So now when we consider an inductor, here the applied input signal will be a voltage. So here we have to apply an voltage. Due to this voltage, there will be a current that is represented by I. Okay. Now this forms an closed loop. Now in this loop, we can apply Kirchhoff's voltage law. To apply Kirchhoff's voltage law, we have to put plus minus along the direction of current flow. Okay. So now when we are applying Kirchhoff's voltage law, we can start it from here. Okay, and we have to go through this circuit like this, and we have to end at the same point. So when we start at this point, if you are going like this, plus to minus, that will be minus. Okay, minus. What about the voltage drop across the inductor? So see here, so these are all the voltage drop across different elements. For inductor, it will be L into di by dt. Okay, so it will be, it is going from plus to minus, so it is minus voltage drop L into di by dt. I is a current flowing through the inductor. Okay, then again we have to go like this. Okay, it is from minus to plus. So for minus to plus, it will be considered as a rise. So here we have to put plus. Plus this drop is, this is nothing but an voltage source. Okay, so this will be voltage rise, that is plus V. Okay, that is equal to 0. Now if you are rearranging this, we get V is equal to L into di by dt. Now listen here. So this equation is input torque T is equal to J into first derivative of the velocity omega. Okay, so here the input voltage V is equal to L into first derivative of the output current I. Both equations are in the similar form. Okay, now we can say J is equivalent to L. Okay, that is, in mechanical rotational system, J can be replaced by an inductor L in an electrical system. Okay. Similarly, we have to consider the next component of the mechanical rotational system, that is nothing but B. Okay. So here B is nothing but, what is B? B is nothing but the frictional component. Okay, so in this B, what we have to do is we are considering an ideal dash part, okay, which is having only the frictional effect, and here there is no moment of inertia of mass and also the elasticity effect. Okay, so what we have to do is one end of this B is connected to one fixed surface and the other end is free. At the free end, we are applying an input torque. Okay, due to that, there will be a displacement, angular displacement of this frictional element, that is B. So this angular displacement is represented by theta. Along the same direction, there will be an angular velocity that is represented by omega. Okay, so now using Newton's second law, we can write the applied torque T will be equal to the opposing torque due to dash part, that is represented by TP. Here there will be a single opposing torque because this element is having only the frictional effect. Okay, there is an absence of moment of inertia of mass as well as elasticity. Okay, so there will be a single applied force as well as single opposing force. We know the formula for TB. What is TB? B into d theta by dt. Okay, now we have to write this d theta by dt in terms of omega, that is output velocity. Okay, see here d theta by dt will be equal to omega, so directly we can write it as omega. Okay, now the torque G will be equal to B into the output velocity omega. Okay, so now this can be equated to a resistor in an electrical systems. Only when we draw this resistance here, we will get the similar equations. Okay, so here for this resistor R, we have to give an input voltage V. Okay, due to that there will be a current I that is passing through the resistor R. Now we can apply this and closed loop, isn't it? Now we can apply Kirchhoff's voltage law. Okay, so we have to start it from here. So along the direction of current flow, we have to put plus minus. If you are starting from here and if you are going through the circuit like this, from plus to minus, it will be considered as minus. Minus, what about the drop across R? That is I into R. Okay, so see here, this is an voltage drop across the resistor. I into R, that is I into the resistance value. Then if you are going like this, it will be from minus to plus. So it is plus and the voltage here is V, that is equal to 0. Okay, if we are rearranging this, we get V is equal to I into R. Okay, see here in mechanical rotational system, the input torque will be equal to V into output angular velocity. Okay, so here the input voltage V equal to R into the output current I. Both equations are the similar form, that is there is no integration or there is no differentiation here. Okay, now we can say the dash part in mechanical rotational system can be equated to resistor in an electrical system. Okay, so now we are going for the third element, that is nothing but spring. Okay, torsional spring. Here is an ideal spring which is having only the effect of elasticity, so there will be an opposing torque due to elasticity, that is nothing but dk. There is an absence of J as well as B, so there will not be any opposing torque due to J as well as B. Okay, so this is an ideal spring. So one end is connected to the fixed surface and the other end is free. At the free end, we are applying an input torque. Okay, so due to this torque, there will be an output angular displacement theta. In the same direction, there will be an angular velocity that is represented by omega. Okay, so now using Newton's second law, we can find the torque acting on a body, that is applied torque will be equal to opposing torque. Here there will be a single opposing torque Tk, that is equal to K into theta. This is the formula. Okay, now we are going to write this theta in terms of omega. Okay, see here this theta will be equal to integral omega dt. So directly we can write it as integral omega dt. Okay, so now we are going to transform this into electrical component. Okay, so here in the electrical component we have to write the capacitor here. Okay, so if the capacitor is connected to one supply, that is voltage, due to that there will be a current I which is passing through the capacitor. Okay, now along the direction of current flow, we have to put plus minus. If you are after writing this plus minus, what we have to do? We have to apply the law. Okay, we can start from here. When we are going from plus to minus, it will be minus. What about the voltage drop across the capacitor? 1 by C into C here, 1 by C into integral I dt. Okay, so 1 by C into integral I dt. Now we have to go through the circuit like this. From minus to plus, it will be plus. This voltage is V. Okay, V is equal to 0. If you are rearranging this, we will get V is equal to 1 by C into integral I dt. Okay, so from this we say that this in mechanical rotational system, the input torque will be equal to K into integration of the angular velocity. Okay, similarly in electrical system, the input voltage V will be equal to 1 by C into integration of the output current I. Okay, so we can equate this K, that is spring in mechanical rotational system, into a capacitor in an electrical system. Okay, quantity wise it will be, that is elasticity coefficient K will be equal to reciprocal of the capacitance value, but the component wise K will be equated to the capacitor C in an electrical systems. Okay, so in mechanical rotational system we have used this Newton's second law. But here what we have to do, we have to apply the Kirchhoff's voltage law in torque to voltage analogous circuit. Okay, so from these concepts we can write the formula like this. Okay, so torque is equated to voltage in torque to voltage analogy, then velocity is equated to current. Okay, these represents the inputs. Okay, now what about the different components? J can be equated to L. Okay, J is equal to L, and B can be equated to R, and K can be equated to C, but quantity wise it will be the reciprocal. Okay, so now we will see about the next analogy, that is torque to current analogy. Okay, that is nothing but T to I analogy. Okay, so here what we have to do is we are going to transform each and every element in this mechanical rotational system into electrical system based on this torque to current analogy. Okay, so in the mechanical rotational system, what's the input signal? That is nothing but twisting force, that is torque. Okay, then electrical system, what's the input signal? That is current, because it's a torque to current analogy. Okay, then what about the output signal for mechanical rotational system? Rate of change of angular displacement, that is nothing but angular velocity. Okay, what about the output for electrical system? That's an voltage, because input we considered it as an current. Okay, so now we are going to convert each and every element into the corresponding electrical system. So similar to the previous analogy, we are going to consider the moment of inertia of mass. This is an ideal moment of inertia of mass. So it is not having any frictional as well as elasticity effect. So one end of this moment of inertia of mass is connected to a fixed surface, other end is free. At the free end we are applying an input applied torque T. Due to this there will be an angular displacement theta. Along the same direction there will be an angular velocity, that is omega. Okay, now this applied torque will be opposed only by this opposing torque due to moment of inertia of mass, that is Tj. Okay, there will not be any Tb as well as Tk. Now using Newton's second law we can find the torque which is acting on a body, that is applied torque T will be equal to the opposing torque Tj, that is equal to J into, this is the formula, d square theta divided by dt square. Now using this relation, d square theta divided by dt square can be written as d omega by dt. Okay, so j into d omega by dt. Okay, now we are going to convert this into an electrical component. Okay, so here we are going to consider an capacitor. Only when we use an capacitor here we get the similar form of equations. Okay, so now for the capacitor we have to give an input. Here the input is an current, so it should be connected to a current source. Due to this there will be a current through the capacitor, and which causes an voltage drop across the capacitor. Okay, now here we are going to apply an Kirchhoff's current law in torque to current analogy. So here there will be a node, isn't it? In this node, what about the incoming current? I. What about the outgoing current? Current going through the capacitor. So what is Kirchhoff's current law? Incoming current will be equal to outgoing current. Here the incoming current is I, that is equal to outgoing current flowing through the capacitor. What's the current flowing through the capacitor? See here, I is equal to C into dV by dt, that is C into dV by dt. Okay. So now here in mechanical rotational system, the input torque will be equal to J into first derivative of the output velocity. Okay, here also the input current I will be equal to C into first derivative of the output voltage V. So from this we can say J is equivalent to C. Okay, similarly we have to convert the next element. The next will be an dash part. Okay, so in the dash part, this is an ideal dash part. There will be an opposing torque only due to dash part. There will be an absence of moment of inertia of mass as well as elasticity effect. Okay, so now one end is free. and other end is connected to the fixed surface. At the free end, we are applying an input torque. Due to that, there will be a displacement theta and also there will be a velocity omega. Okay. Now, using Newton's second law, we can find the torque which is acting on the body. That is, applied torque will be equal to opposing torque TB. Okay, because there is a single opposing torque here. What's the formula for TB? B into d theta by dt. Now, we can write this theta in terms of omega. See here, d theta by dt can be directly written as omega. Okay, so this will be equal to B into omega. Now this can be equated to an electrical component resistor. Okay, so here we have to connect the resistor in a current source because the input is a current. Due to the current flow, there will be a drop across the resistor. Okay. Now, at this node, we are going to apply Kirchhoff's current law. Incoming current I will be equal to outgoing current is nothing but current flowing through the resistor. What about the current flowing through the resistor? I is equal to V by R. Okay. V is an voltage drop across the resistor. V divided by the resistance value. Okay. So this can also be written as 1 by R into V. Okay. So now see here, these two equations are in the similar form. That is, input torque will be equal to B into output velocity. Here the input current will be equal to 1 by R into output voltage. Okay. Now we can equate a B in mechanical translational system into R in electrical system. But the quantity wise, the frictional coefficient will be the reciprocal of the resistance value. Understood? Now we have to transform the third element, that is nothing but K. So this is an ideal spring, okay, torsional spring. So here one end is connected to the fixed surface, other end is free. At the free end, we are applying a torque. Okay, so this is not this is having only an elasticity effect. There will not be any moment of inertia of mass as well as friction. Okay, so there will be a single opposing force, that is Tk. Using Newton's second law, we can find the torque acting on this body. That is, applied torque T will be equal to a single opposing torque, that is Tk. What's the formula for Tk? That we know, K into theta. Now we can write the value of theta in terms of omega. See here, theta is equal to integral omega dt. Okay, so instead of theta, we can write it as integral omega dt. Okay, so this can be transformed into an electrical component inductor. Okay, then only we get the similar form of equation. So when we connect an inductor here with an current source I, what happens? There will be a current through the inductor and it causes an voltage across the inductor, that is V. Okay. Now at this node, we are going to apply Kirchhoff's current law. So when we apply Kirchhoff's current law, incoming current will be equal to the outgoing current, isn't it? What about the incoming current here? That is current I. What about the outgoing current? Current flowing through the inductor. Okay. I see here. What about the current flowing through the inductor? All these are formulas. Okay, you have to study these formulas. 1 by L into integral V dt. Okay. So here we can write 1 by L into inductor value into integral voltage drop across the inductor V into dt. Okay, now these two equations are in the similar form with the integration. Okay, applied torque T will be equal to K into integration of the angular velocity, and here the input current I is equal to 1 by L into integration of the output voltage. Okay, now these two are in the similar form, so we can equate K into 1 by L. Okay. Here the quantity wise, this elasticity coefficient K will be inversely proportional to this inductance value, or elasticity coefficient K will be the reciprocal of the inductance value, but the element wise we can equate the spring to an inductor in electrical system. Okay. Now, what about the law used in this mechanical rotational system? That is Newton's second law. Okay. What about the law in electrical system? So it is a Kirchhoff's current law. We used Kirchhoff's current law to derive the equations. Okay, in torque to current analogy. Now from this we can form the formula like this. Okay. For torque to current analogy, torque is equated to current and velocity is equated to voltage. It's an angular velocity, so this is an voltage. Now J will be equated to C and V is equated to R, but quantity wise it will be 1 by R. K is equated to inductor. Okay, quantity wise it will be 1 by L. So in this formula, in the left hand side of this arrow, it represents the mechanical rotational system. Okay, in the right hand side of this arrow represents the different components of electrical systems. Okay. So now these all are the formulas we derived in this electrical analogous to mechanical rotational system. Okay, here we have two analogy, torque to voltage analogy as well as torque to current analogy. Similarly, we know the relation between angular displacement theta as well as angular velocity omega. Okay, this you have to remember to solve the problems. And also we know the relation between voltage as well as current for the different electrical components, that is resistor, capacitor as well as inductor. Okay, so these you have to study. If you know all these formulas, we can easily solve the problems related to electrical analogous to mechanical rotational system. Okay. Now we will see the problem in this electrical analogous to mechanical rotational system. Okay, so this is the question. Write the differential equation governing the mechanical system shown and draw the torque to voltage as well as torque to current electrical analogous circuit and verify by writing mesh and node equations. Okay, so in the previous lectures we have seen how to find the electrical equivalent of mechanical translational system, isn't it? Where we had the two analogous circuit, that is force to voltage as well as force to current analogous circuit. Okay, now here we have torque to voltage as well as torque to current electrical analogous circuit. Okay, so this is the question. So this is a mechanical rotational system. By seeing the diagram itself, we can easily identify because it uses the different components of mechanical rotational system. Okay, J, B as well as K. Similarly, the input signal here is a torque. Okay, so now what we have to do here, first we have to find the differential equation. That's a basic steps in all the analysis. First we are finding the differential equation using the free body diagram. Okay, mainly we are going to find the electrical analogous circuit. Okay, so here in electrical analogy, for each and every moment of inertia of mass, J1, J2, J3, these three are the reference elements. Okay, for each reference elements, we have to mark the outputs. Okay, so here what about the output signal? Output is a rate of change of angular displacement. That is nothing but angular velocity. Okay, angular velocity will be represented by omega. Okay, so now for each mass, that is moment of inertia of mass J1, J2, J3, in addition to this angular displacement theta, we have to represent the angular velocity omega. Okay, for J1, we can assume the angular displacement as theta 1. Immediately after this J1, along the same direction, there will be a rate of change of displacement. That is nothing but omega. Okay, omega 1. Similarly, for J2, it will be theta 2 as well as omega 2. For J3, it will be theta 3 as well as omega 3. Okay, so by redrawing the diagram, we have to mark all the outputs. Okay, without marking the outputs, we cannot proceed the problem. Okay, so in this question, the input as well as output should be there. Okay, then only we can proceed. Now what we have to do, first we have to identify the input and we have to write it, isn't it? So here the input will be an torque, so we can represent it as capital T. Okay, this is nothing but D of T, but simply we can write it as capital T. Okay, input as well as output all varies with respect to time. Okay, now what about the output displacements? For each and every reference element, the output displacement will be theta 1, theta 2 as well as theta 3. Okay, and the corresponding output velocities are omega 1, omega 2 as well as omega 3. Okay, now what we have to do, this is similar to the electrical analogous to mechanical translational system. Okay, only there will be changes in the input as well as output. Okay, first we are going to draw the free body diagram for moment of inertia of mass J1. Okay, listen here. So this is an free body diagram for moment of inertia of mass J1. Okay, so see here, this is a question. Okay, so to make you understand, I have given a number of formulas as well as diagrams in the right side. Okay, no need to draw all these things again and again. This is already there in your notebook. Okay, so here while drawing the free body diagram, what we have to do, first we have to draw a free body, the moment of inertia of mass J1 inside a single box. Then in the left side as well as right side, we have to put a line, isn't it? Now we have to see the question. So this is a question. When we consider this moment of inertia of mass J1, what will be the applied torque? Here there will be an applied torque which is directly connected to this moment of inertia of mass J1. Okay, that is nothing but capital T. Okay, so first we have to mark this applied torque here. Okay, in the left side of this J1. Similarly, immediately after this J1, what we have to do? We have to mark the output angular displacement, that is theta 1. Okay. In addition to that, we have to represent this omega 1 also. Okay. So here you should represent this omega 1 also. Understood? So now what about the opposing torques? Now in the right side of this J1, we have to mark all the opposing torques. Okay. So now what about the own opposing torque, that is represented by Tj1. Then what are the elements which are connected to this J1, that is B1 as well as K1. Okay. So none of the elements which is connected only to this J1. Okay. This K1 as well as B1 are connected between J1 as well as J2. Okay. So what we have to do? We have to draw all the opposing forces one by one here. Okay. So first one is the own opposing force, that is nothing but Tj1. Then TB1. That is connected between J1 and J2, TB1, as well as the next element is K1, that is TK1. Okay. After drawing the free body diagram, we have to write the formula for each and every opposing torques. Okay. What's the formula for Tj1? We know that is J1 into T square theta 1 divided by dt square, because here the output is an angular displacement theta 1. Okay. D square theta 1 divided by dt square. Then what about the next opposing torque? TB1. What's the formula for TB? B into d theta by dt, isn't it? So here we have to see where this B1 is connected. B1 is connected between J1 and J2. So what we have to do? We have to write the difference in displacement here. Okay. So capital B1 into d by dt of, first you have to write theta 1, then you have to write theta 2, because we are drawing the free body diagram for J1. Okay. So its corresponding displacement should come first, then the angular displacement for J2. Okay. Now what about the next opposing torque, that is TK1. TK1 will be equal to, what's the formula? K into theta. Okay, so here it is K1, so K1 into theta. So but here K1 is connected between J1 as well as J2. Okay, so you have to write the difference in displacement, theta 1 minus theta 2, because we are drawing the free body diagram for moment of inertia of mass J1. So the corresponding displacement should come first. Okay. So after writing these equations for opposing torques, we have to apply Newton's second law, okay, to find the torque which is acting on a body. So what is Newton's second law? Sum of all the applied torque is equal to the sum of the opposing torque. So here there is a single applied torque and the remaining all are opposing torques. Okay. So Tj1 plus Tb1 plus Tk1 is equal to capital T. Okay. Now we have to substitute the value of each and every opposing torque. These are all the values of opposing torques. When we substitute all the values, we get the equation like this. So this is nothing but equation A. Okay, that's a differential equation for the mechanical rotational system due to the moment of inertia of mass J1. Okay. Now what we have to do? Similar to the electrical analogy of mechanical translational system, here we are going to replace each and every theta by means of omega, because we are considering the output as an rate of change of displacement, that is nothing but angular velocity. Okay, omega. So now this equation is in terms of theta. Now we are going to replace this by omega. On replacing displacement theta by omega, what we have to do? We have to use this formula. This formula we know, isn't it? Now instead of this is J1 into d square theta 1 divided by dt square. What is d square theta by dt square? That can be written as d omega by dt. So d square theta 1 divided by dt square can be written as d omega 1 divided by dt. Okay, plus the second element b1 into this can be written as d theta 1 by dt minus d theta 2 by dt. Okay, see here, what is d theta by dt? Omega. So d theta 1 by dt will be omega 1 minus d theta 2 by dt will be omega 2. Okay, plus k1 into, then what about theta in terms of omega? Theta will be integral omega dt. Okay, so integral for theta 1 it will be omega 1 minus omega 2 into dt, that is equal to capital T. Okay, so now we can consider this as an equation number 1. Okay, similarly we are going to draw the free body diagram for moment of inertia of mass J2 as well as J3. Okay, Listen, so this is the free body diagram for moment of inertia of mass J2. Okay, so first we have to draw this J2 in the left side as well as right side. We have to put a line. Okay, now we have to see this question. Okay, so here this is J2. For this J2, is there is any applied torque? No, okay, applied torque is only connected to this J1. Okay, it is not connected to J2. So there is no applied torque here. No need to mark the applied torque. Okay, so here what about the outputs? Output will be theta 2 as well as omega 2. Omega 2 is an output. In addition to theta 2, we are representing this omega 2. Okay, so here you have to write theta 2 as well as you should write this omega 2 also. Understood? It is not shown here, but here you have to show this omega 2. Okay, now in the right side you have to represent all the opposing torques. Okay, so how will you find the opposing torques? So there will be an own opposing torque due to J2, that is nothing but dJ2. Okay, then the elements that is connected only to this J2 will be nil, isn't it? None of the element is connected only to this J2. Okay, but three elements are connected between J2 as well as J1 and J3. Okay, so here TB2 is nothing but the element which is connected between J2 as well as J3. So TB2, then TK1 as well as TB1. Okay, so these are all the opposing torques. Now we have to write the formula for opposing torque. Tj2 will be equal to J2 into d square theta by dt square. D square theta 2 divided by dt square. Okay, because here the displacement is theta 2. Okay, now what about the value of TB2? So to write the value of TB2, we have to see where this B2 is connected. Okay, B2 is connected between J2 as well as J3. So we have to write the difference in displacement here. Okay, so first we have to write this theta 2, then you have to write this theta 3. Okay, because we are drawing the free body diagram for J2. Understood? The next, what is TK1? This K1 is connected between J2 and J1. Okay, so we have to write the difference in displacement. The formula for TK will be K into theta. So theta can be written as theta 2 minus theta 1. Understood? Then TB1. B1 is connected between J2 and J1. So we have to write the difference in displacement. Formula for TB1 is B1 into d theta by dt. Instead of theta, we have to write it as theta 2 minus theta 1. In this way, we can write the formula for all the opposing torques. Now, using Newton's second law, we can find the torque acting on a body, that is sum of all the opposing torque will be equal to 0, because here there is no applied torque. Okay, now you have to substitute the value of all the opposing torques. When we are substituting the value of opposing torque, it will be like this. Okay, this is equal to 0. Now this is equation number B. Okay, so now what we have to do, we have to replace each and every theta by omega. Okay, for that you have to use the relation between theta and omega. So on replacing theta by omega, this will be first term J2 into d square theta 2 divided by dt square can be written as d omega 2 divided by dt. Okay, plus B2 into, this can be split into d theta by dt minus d theta 3 by dt. Okay, what is d theta 2 by dt? That is omega 2. Okay, using this relation. Now, what is d theta 3 divided by dt? That is omega 3. Okay, the next element is plus B1 into d theta 2 by dt is omega 2 minus d theta 1 by dt is omega 1 plus K1 into what about theta in terms of omega? That is integration using this relation. Okay, integral, here we have theta 2 minus theta 1. So we can write it as omega 2 minus omega 1 into dt. That will be equal to 0. Okay, we can mark it as equation number 2. Okay, now similarly we are going to find the moment of inertia, free body diagram for moment of inertia of mass J3. Okay, to draw the free body diagram, first we have to draw this mass J3. Then in the left side as well as right side, we have to put a line. Okay, so in the left side we have to represent the input as well as output. In the right side we have to represent all the opposing torques. Okay, see this J3 here, the torque input is not directly connected, so there is no applied torque here. Then for this J3 there will be an outputs theta 3 as well as omega 3. Here theta 3 is given, you should represent this omega 3 also. Okay, now what about the opposing torques here? The opposing torque will be its own opposing torque, that is Tj3. Then TK3 that is connected only to this J3. Okay, TK3 as well as TB2. Okay, these three are the opposing torques. Now we have to write the value of each and every opposing torques. What is TJ3? TJ3 is J3 into d square theta 3 divided by dt, because here the displacement is, angular displacement is theta 3. Okay, now what is TB2? B2 is connected between J3 as well as J2. Okay, so we have to write the difference in displacement, that is B2 into d by dt of theta 3 minus theta 2. Now we are drawing the free body diagram for J3. So this theta 3 displacement should come first. Okay, theta 3 minus theta 2. Then what about the value of K3? Here K3 is connected only to this J3. Okay, it is not connected to J2 as well as J1. So directly we can write the formula. What's the formula for Tk? K into theta. So here Tk3 will be K3 into the displacement is theta 3. So we can write it as theta 3. Okay. Now, using Newton's second law, we can find the torque acting on the body. So, what about the torque acting on the body? Sum of the applied torque equal to opposing torque. Here, there is no applied torque. All are opposing torques. Sum of all the opposing torque will be equal to 0. Okay. Now, we have the formula for each and every opposing torque. We have to substitute it here. Okay. So, we get the equation like this. That is equation number C. Okay. So, now what we have to do? We have to replace this theta by omega, because here we are considering the output as an omega. Okay, so using this relation we can easily convert theta into omega. Okay, so here for the first element J3 into what is d square theta 3 divided by dt square, that is d omega 3 divided by dt. Okay, then B2 into, this can be split into 2, d theta 3 divided by dt, that is nothing but omega 3, then d theta 2 divided by dt, that is nothing but omega 2. Okay, plus K3 into, this theta can be written in terms of omega as integral. Okay, so integral omega dt, that will be equal to 0. So this is equation number 3. Okay, now till this we have derived 3 differential equations governing the mechanical rotational system for moment of inertia of mass J1, J2 as well as J3. Okay, so now what we are going to do is we are going to obtain the electrical analogous circuit. Okay, the first analogy is a torque to voltage analogy, G to V analogy. So first you have to write the formula. Okay, so this is the formula we studied. We have to write the formula. Then by using the question, that is problem, we are going to obtain the corresponding equivalent electrical circuit. Okay, so here this is a torque to voltage analogy. So we are going to apply Kirchhoff's voltage law. To apply Kirchhoff's voltage law, we need an loop. Okay, so what we have to do is each and every reference element J1, J2 and J3 corresponds to a loop in electrical system. Okay, so corresponding to J1, J2 as well as J3, here you have to consider 3 number of loops. Okay, so for the first loop, so this first loop is for J1, second loop is for J2 and third loop is for J3. Okay, so the elements which is connected only to this J1 should be drawn here as well as here. Okay, and the elements which is common to both J1 and J2 should be drawn here, and the element which is connected only to J2 should be connected here, and the element that is connected between J2 and J3 should be connected here. Okay, in series. Now the elements which is connected only to this J3 should be connected here and here. Okay, so no need to connect any elements here because this will be considered as a ground. Okay, now we have to see the first moment of inertia of mass, that is nothing but J1. Okay, so here for this J1, similar to drawing an free body diagram, what we have to do, we have to say all the opposing torques, isn't it, as well as applied torque. Okay, so for this moment of inertia of mass J1, the applied torque will be T. Is it right? So here the T will be converted into the voltage. Okay, so in the corresponding electrical equivalent circuit, we have to draw an voltage source here. Okay, with positive in the upper side as well as negative in the lower side, because this is a ground. Okay, now what we have to do, So this is an applied torque. Then what are the opposing torques? Here the opposing torques are due to own moment of inertia of mass J1. So J is equated to inductor L. So correspondingly we have to draw this L1. Okay. Then none of the element is connected only to this J1. Okay. So we have to see what are the elements connected between J1 and other masses. So here K1 as well as B1 are connected between J1 as well as J2. Okay. So K corresponds to, what is K? K corresponds to C in electrical circuit. Okay. So for this K1 we have to draw this C1. Understood? Which is common to both J1 as well as J2. So here it should be drawn in the path here. Okay. This path is common to, or this branch is common to loop 1 as well as loop 2. Okay. So here you have to draw the C1. Understood? Now the next element is B1. This is also connected between J1 and J2. Okay. So B corresponds to R. So the resistor should be connected in the common branch. Okay. For this loop 1 as well as loop 2. Understood? So in this way we can complete all the elements of this loop 1. Okay. Similarly, we have to see this J2. Okay. In this J2, is there any applied torque? No. Torque is applied to this J1 only. Okay. So if you are having any applied torque for this J2, first you have to mark the voltage source here, corresponding voltage source here. Okay. So with positive sign in the right side as well as negative sign in the left side. Okay. Then only it will match the direction of current flow. Okay. So here there is no applied torque. So there will not be any voltage source in this second loop. Okay. Now what are the opposing torques? Its own opposing torque, that is due to J2. J corresponds to L. So here you have to draw this L2. Okay. So this is only for loop 2. Okay. The next, none of the element is connected only to this J2. Then the remaining are connected between the J2 mass as well as other masses. Okay. Now, what about B2? B2 is connected between J2 as well as J3. Okay. In the common branch between loop 2 as well as loop 3, we have to connect the corresponding equivalent element. Okay. B2 corresponds to, what is B? B corresponds to R. So B2 corresponds to R2. So it should be drawn in the common path between loop 2 as well as loop 3. Because here B2 is connected between J2 as well as J3. Understood? Now what about this K1 as well as B1? K1 and B1 is also connected to this J2 as well as J1. Okay. This K corresponds to C. So already we have represented this C1 here. Okay. Similarly, B corresponds to R. Already we have drawn this R1 here. Okay. So no need to draw these elements again and again. Okay. So now this loop 2 is completed. Okay. Now we have to complete this loop 3. So to complete this loop 3, what we have to do? We have to see this moment of inertia of mass J3. Here there is no applied torque, isn't it? Applied torque is connected only to this J1. So no need to draw an voltage source here. Suppose if you have an applied torque here, what we have to do? Initially here you have to put the voltage source with positive in the right side and negative in the left side. Okay. So now what are the opposing torques? Its own opposing torque due to J3. That is nothing but J corresponds to L, isn't it? So here you have to draw this L3. Understood? Now, the element which is connected only to this J3 is K3. K corresponds to C. Okay. So here you have to draw this C3. Here, instead of drawing C3 here, here also we can draw. Okay. So this is the element which is connected to this J3 only. Then B2. B2 is connected between J3 as well as J2. So it should be drawn between loop 3 as well as loop 2. Okay. B corresponds to R. So in here it is B2. So it will be R2. It should be drawn between loop 2 as well as loop 3. Already we have drawn this one. That is the resistor R2. No need to draw it again. Okay. So in this way we can complete all the components in this loop 3. Okay. So after representing each and every element, what we have to do is we are going to apply this Kirchhoff's voltage law. Okay, in each and every loop. Before applying this voltage law, what we have to do? Along the direction of current flow, we have to put plus minus, plus minus, plus minus, plus minus, etc. Okay. Similarly, in this loop 2 also, we have to put plus minus for each and every element. Okay. In this loop 3 also, we have to put every plus minus for every element. Okay. Always take the direction of current flow in a clockwise direction. Okay. take the current flow in the clockwise direction. Now, when we consider this branch here, for each and every element, there will be two number of polarities, okay? Because this I1 is flowing from top to bottom. Then I2 is flowing from bottom to top, okay? Here also there will be two currents, okay? So now what we are going to do is, we have to apply Kirchhoff's voltage law on this loop 1, okay? So listen here, we can start it from any point, okay? We can here we can start it from here, and we have to go through the different elements like this, and we have to finish at the same point, okay? So now what we have to do, when we are starting from here, from plus to minus, it will be minus. What about the voltage drop across this L1? Listen here, voltage drop across this inductor L will be L into di by dt. Okay, so here it is L1 into di1 divided by dt, because I1 is the only current flowing through this L1. Okay, so now what we have to do is, we have to go for a next element, that is nothing but C1. So here, when we are moving from plus to minus, it will be minus. What about the voltage drop across the capacitor C1? See here, this is the formula. 1 by C into integral I dt. That is 1 by C1 into integral I is a current flowing through the C1, isn't it? Two currents are flowing. Okay, I1 as well as I2, but in the opposite direction. So we have to write the difference in current, I1 minus I2, because we are writing the equation for loop 1. So this loop 1 current should come first, I1 minus I2 into dt. Okay, the next element will be resistor R1. When we are going from plus to minus, it will be minus. What about the voltage drop across the resistor R1? See here, I into R. That is R1 into current. Current is nothing but the difference in current, okay? Because two currents are flowing, I1 minus I2. Okay, then we are going like this. Minus to plus, it will be plus Vt. Okay, V of t, that is the applied voltage, that will be equal to 0. Understood? Now this is the only voltage rise component, so we have to bring it to the right side. Now in all the elements we have a minus sign, so throughout we can multiply it with minus, so we will get the equation like this. Okay, we can represent this as equation number 4. Okay, similarly for this loop 2, we are going to apply Kirchhoff's voltage law. Okay, so when we are starting from here, at this corner, going from plus to minus, it will be minus L2 into, what about the voltage drop across the inductor? See here, L into di by dt. Okay, that is L2 into I2 divided by dt, because I2 is the only current through this L2. Then if you are going like this, from plus to minus, it will be minus R2 into, what about the current flowing through R2? Two currents, that is I2 and I3. So first you have to write this I2, because we are writing the equation for loop 2. I2 minus I3. Minus, then here again it is plus to minus, so that will be minus R1 into, here also two currents flowing through this R1, isn't it? I2 minus I1. Okay, then again plus to minus will be minus 1 by C1 into, that is an voltage drop across the capacitor, integral I dt. I is nothing but difference in current, I2 minus I1 into dt, that is equal to 0. Okay, now in this equation we have minus throughout, so we can multiply throughout by minus sign, so we will get the equation like this. Okay, now for loop 3, we are going to apply Kirchhoff's voltage law. Okay, we can start it from here, from plus to minus, it will be minus. Voltage drop across the inductor L3 will be L3 into di3 by dt, because I3 is the only current flowing through this L3. The next plus to minus, it will be minus. What about the voltage drop across the capacitor? 1 by C3 into integral I3 dt. I3 is the current flowing through this C3. Okay, now again from plus to minus, it will be minus R2 into that is two currents are flowing through this R2, that is I3 as well as I2. So we have to write the difference in current, I3 minus I2, because we are writing the loop equation for loop 3. Okay, so its current should come first, I3 minus I2 is equal to 0. So for each element we have minus sign, so throughout we can multiply it with minus, so it will become plus. Okay, now this will be equal to 0. So this is equation number 6. Now these three equations, that is equation for loop 1, loop 2, loop 3, are compared with the previous three equations, that is derived for mechanical rotational system for mass J1, J2 as well as J3. Okay, equation 1 will be equivalent to 4, 2 will be equivalent to 5, and 3 will be equivalent to 6. Okay, so we can write it as The equation 4, 5 and 6 are equivalent to equation 1, 2 and 3 respectively. Okay. So in this way we can obtain the torque to voltage analogy analogous circuit, okay, for a given mechanical rotational system. Similarly, we can obtain the torque to current analogous circuit. Okay. So the next one will be a torque to current analogy. So first we have to write the formula for torque to current analogy. Okay. So here there will be a slight change. Okay, that you have to remember. Now from the question we can easily draw the electrical equivalent circuit. Okay. So in torque to current analogy we are going to apply Kirchhoff's current law. To apply Kirchhoff's current law, what we need? We need a node. Okay. So here a number of masses or the reference elements will correspond to a node here. Okay, so here there will be a 3 number of moment of inertia of mass J1, J2 and J3. So correspondingly here you will have 3 number of nodes. Okay, node 1, node 2 and node 3, and also we have to consider the reference node, that is ground node. Okay, for each node you have to put a line like this. For node 2 also we have to put a line. Okay, for node 3 also we have to put the line. Then only we can connect each and every element to this node 1, 2 as well as 3. Okay, for node 1 we have to assume the voltages V1. For node 2 we have to assume the voltages V2. For node 3 we have to assume the voltages V3. Okay, now we can draw each and every element. Okay, so listen here. For this J1, the applied torque input is directly connected. Torque corresponds to current. So here this an input, isn't it? So we have to draw the current source for this node 1. Okay, so for this node 1 we have to draw a current source. We cannot draw this current source only to this node 1, so it will be connected with respect to ground node. Okay, so while drawing this current source, what we have to do is the arrow should be away from the ground node. Okay, and it should be towards the particular node. Okay. Now what we have to do, we have to draw other elements. So here what about the opposing torques? Its own opposing torque. Okay, due to J1, J corresponds to C, isn't it? So we have to draw the capacitor C1 at this node 1. Okay, this is due to the own opposing torque. Now what about the other opposing torques? TK1 as well as TB1, isn't it? K corresponds to L. Okay, so we have to draw L1 in between V1 as well as V2, or the node 1 as well as node 2, because K1 is connected between J1 and J2, isn't it? So we can draw this L1 in between node 1 as well as node 2. Then B1, B corresponds to R. B1 is also in between J1 and J2. So we have to connect this R1 in between 1 as well as 2. Okay. So now in this way we can complete all the elements in this node 1. Now see this J2, in this J2, is there is any applied torque? No. If you are having any applied torque, the corresponding current source should be drawn here. Okay. So now there is no applied torque, all are opposing torques. Now what about the own opposing torque due to J2? That is nothing but J corresponds to C. Okay, here for the J2 it will be C2. So we have to connect the C2 between that particular node as well as ground. Okay, then none of the element is connected only to this J2. Then all are the elements connected between the various moment of inertia of mass. Okay, for this J2, this B2 is connected between J2 and J3. Okay. B corresponds to R. So R2 should be connected between node 2 as well as node 3. Okay. Now here K1 as well as B1 are connected between J2 and J1. K corresponds to L. Okay, this is already connected between node 2 as well as node 1 as well as K as well as B. The B is nothing but B corresponds to R, isn't it? R1. That is also connected between node 2 as well as node 1 already. Okay, so no need to connect these two elements again and again. Okay. In this way, we can complete all the elements corresponds to this node 2. Now see this node, that is moment of inertia of mass J3. So here in this J3, there is no applied torque. So no need to connect any current sources here. What about the opposing torques? Its own opposing torque due to J3. J corresponds to C. So C3 can be drawn like this in between ground node as well as that particular node 3. Okay. Now K3 is the component which is connected between J3 as well as reference. That is the element which is connected only to this J3. Okay. So this K3 corresponds to L3, isn't it? Because K corresponds to L. So L3 should be connected between the node 3 as well as ground node. Okay. Now here, listen here, this is another one opposing torque due to B2. B corresponds to R. So B2 means R2, which is connected between node 3 as well as node 2. This is already connected. So no need to connect it again. Okay. So in this way, we can complete each and every element of this node 3. Okay. Now what we have to do? We have to apply the Kirchhoff's current law. Okay, so to apply this Kirchhoff's current law, we have to assume the current direction for each and every node. Okay, so here for this node 1, this IFT is a current source. Okay, so this is always towards the node. For all the other currents, we have to assume the direction as away from the node. Okay, so this should be away from the node. All these currents should be away from the node. In this node 2, there is no source like this. So there will not be any incoming current. All currents we have to assume it as an outgoing current, that is away from the node. Now consider this node 3. Here there is no current source. So all are the outgoing currents. We have to assume like this. Okay. Similar to the clockwise direction of current in loop for torque to voltage analogy. Here for each and every node, we have to assume the current which is away from the node. Okay. Now in node 1, we can apply Kirchhoff's current law, KCL. Okay. So in Kirchhoff's current law, incoming current will be equal to sum of the incoming current will be equal to the sum of the outgoing current. Okay. What about the incoming current here? There's a single incoming current, that is I of t. So this I of t will be equal to, what about the outgoing currents? 3 number of outgoing currents. Okay, so we have to write each and every outgoing current by using this formula. So this is the formula for the current flowing through each and every element. This you should study. Okay, then only we can write all these equations. Now what about the current flowing through the capacitor? C1 into C here, C into dV by dt. This V is nothing but voltage drop across the capacitor C. Okay, so here it is C1 into d by dt of V1. What is V1? Voltage drop across the capacitor C1. So for this capacitor C1, one end is at V1 voltage, other end is at ground voltage. Okay, so V1 minus 0 because the current is flowing in this direction. Okay, so V1 minus 0 is nothing but V1. So we can write it as dV1 by dt. Okay, then plus next the resistor R1. What about the current flowing through the resistor R1? See here, V by R. Okay, so that is, or we can write it as 1 by R into V. Okay, so here it is 1 by R1 into what is V? V is nothing but, this V is nothing but voltage drop across the resistor R. Okay, what about the voltage drop across the resistor R1? Here we are considering this arrow because we are writing the equation for node 1. Okay, so this is a higher potential, V1 minus V2. Okay, we can write it like this. Now what about the third current? That is current flowing through the inductor L1. What's the formula? 1 by L into integral V dt. Okay, 1 by L1 into integral, what is V? Voltage drop across the inductor L1. So here we are considering this arrow. This is a higher potential V1. This is a lower potential V2. So V1 minus V2. Okay. So this will be the current flowing through the inductor. So in this way, we can get the 7th equation. Okay. So now similarly for node 2, we have to apply Kirchhoff's current law. Okay. So in node 2, when we apply Kirchhoff's current law, what about the incoming current? None of the incoming current, isn't it? All are outgoing currents. 4 currents are outgoing currents. So sum of all the outgoing currents will be equal to 0. Now we have to write the formula for each and every current. Okay. So here first we can write the current for the C2. What's the formula for current flowing through the capacitor? I is equal to C into dV by dt. Okay, the C2 into d by dt of V2. V2 is nothing but voltage drop across the capacitor C2. So here the drop is V2 minus 0. So we can write it as V2. Okay, now this L1, what about the current flowing through the inductor L1? See the formula, 1 by L into integral V dt. So 1 by L1 into integral. So we have to consider this arrow. Okay, because we are writing the equation for node 2. So V2 minus V1 dt. Okay. Now what about the current flowing through this R1? 1 by R1 into, what about the voltage drop across the resistor R1? We have to assume this current direction, V2 minus V1. Okay, now we can write the current for this R2, that is 1 by R2 into, what about the voltage drop across this R2? We have to assume this current direction, that is V2 minus V3, because current flowing from higher potential to lower potential. Okay, V2 minus V3. Okay, that is equal to 0. In this way we can write all the 4 currents. Okay, here there is no incoming current, so one side of the equation will be 0. Okay, this is equation number 8. Okay, Now, in this loop, node 3, we can apply Kirchhoff's current law. Okay. So here, what about the current flowing through the capacitor C3? I is equal to C into dV by dt. Here it is C3 into d by dt of, what about the voltage drop across V3? That is voltage drop across C3. That is V3 minus 0. Okay, that is V3. Then what about the current flowing through this L3? 1 by L into integral B dt. That is 1 by L3 into integral of, what about the voltage drop across L3? V3 minus 0, because this is a ground potential. Okay. V3 minus 0, that is nothing but V3 dt. Okay. Now we can consider this R2. R2 is an current flowing through the resistor. R2 will be V by R. Okay. Or 1 by R into V. Okay. So 1 by R2 into, what about the voltage drop across this R2? Now we are writing the equation for node 3. So we have to assume this current direction. Okay. So it is flowing from node 3 to node 2. So V3 minus V2. Okay. That is equal to 0. Now these three equations will be equal to equation 1, 2 and 3, which is obtained for the mechanical translational system. Okay. So we can write equation 7, 8, 9 are equivalent to equation 1, 2 and 3 respectively. Okay. We can compare the equations also. Okay. So in this way, we can find the electrical equivalent circuit for the given mechanical translational system using two analogous circuit, that is torque to voltage analogy as well as torque to current analogy. Okay. So now this is the homework. Okay. So here one mechanical system is shown. You are asked to obtain the electrical analogous circuit using torque to voltage as well as torque to current. Okay. So this is a mechanical rotational system because it uses J, B as well as K. Okay. So the input is torque T of T, or simply we can write it as capital T. Then for every moment of inertia of mass, the output velocity is given. Okay, omega 1, omega 2 as well as omega 3. In addition to this omega 1, omega 2 and omega 3, we can represent theta 1, theta 2 and theta 3 also. Okay, so after marking the input as well as output, we can proceed the problem and we can find the electrical equivalent circuit using torque to voltage as well as torque to current electrical analogous circuit. Okay. So with this, the electrical analogy is over. Okay. The rest we shall see in the next class. Thank you.